Um, homework assignment, right? All right, how did that go? Easy? Hard? Weird? All right, well, I'm going to continue to use Java as our example in here. I know some of you haven't seen a lot of Java before. Everything you need to complete the stuff, I do in class, but if you want to solve it, I think I sent out the email using GameSalad, which is the tool most of you had in CSC325, or even in Excel. That's fine. You know, the punchline here is that the goal of doing this stuff programmatically, as opposed to just learning a formula, is to look at the applied side of the theory. Memorizing formulas doesn't really give you an idea of how something really works. And when we actually write an algorithm to do something, we can see how transitioning between different things makes the pattern move. And we can see that a lot of things are the same. Like today, we're going to be dealing with number conversions between bases. And some of you have seen that before in some of my other classes, but we'll see that the pattern, whether you're converting from decimal to binary or binary to hex or hex to octal, they're all the same. So it becomes kind of interesting, I guess. Any case, so the homework assignment was to create a tool, some sort of tool. Abe, what's up? You're dressed funny.
Thank you.
It's like very casual for you.
Yeah.
Yeah, aren't you usually like kind of more proper and like bow ties and stuff?
Yeah, well.
This is like V-neck, like, hey, I just got off a construction site.
I think they wear V-necks on construction sites.
How would you know?
You weird kid.
Probably because I've probably worked on some.
Oh, have you? What are we eating?
Depends on what you define as a construction site.
Why does what you're eating have to depend on what I put?
Oh.
I'm already onto a new line of questioning.
Meatball sub.
From?
Subline. It's forever. I had 20 minutes before this class started.
That's why you missed the quiz?
There's a quiz.
You missed it.
Bet you know what the answer is.
I'm not going to tell you what it was now.
Let's say the Amish space program.
That probably would have been right. What was that? That was the answer to what was the greatest failure of the 21st century? 20th century. Yeah, it was the Amish space program.
Those goats.
What's up?
The goats, they ruin everything.
I think it may not have been bailed well. Hold on, we got to read that again.
Are there pictures of goats?
Okay, let's see. NASA officials watched in horror Monday as the $68 billion straw space shuttle Explorer 2 burst into flames just after liftoff from Cape Canaveral. The 4 American and 3 Russian astronauts on board were killed instantly despite the protective all-straw spacesuits. The technicians were stunned by this failure, which capped a flawless 6-month pre-launch test period. They count faulty twine among the possible causes of the accident. The straw ship was dry, lightweight, and well-bailed enough to break the Earth's orbit, but inexplicably burst into flame when ignited with 3,000 gallons of rocket fuel, said NASA Chief Engineer George Toshikima. This is a devastating setback for NASA. An estimated 30 birds, 8 voles, and 23 mice who had nested in the ship's outer hull or burrowed homes deep in the straw engines also perished in the blast. The material holding the ship in place was top-quality burlap baling twine, purchased in bulk from Cape Canaveral's leading farm equipment supplier. The straw ship was constructed with over 200,000 bales of U.S.-grade E-straw, baled, tied, and pitched from the NASA's Cape Canaveral farm and stored over the planting season in the launch pad barn. It was nice and crisp and dry, which is the best condition for straw heading away from the Earth's gravitational pull. According to accident reports, the 1/8 inch thick string was possibly not tied tightly enough or not weaved correctly around a critical fuel-delivering gasket, which may have caused the ship to unravel. Toshikima does not believe such a small imperfection could have caused the massive explosion, which we are still trying to determine why it suddenly burst into flames. He said, in all the pre-fueling tests, pre-fueling, the procedure went perfectly, but as soon as we ignited the fuel, it exploded. Why? Some insiders fault a problem that occurred last week when a section of the ship's starboard high-pressure re-entry tiles were eaten by a horse. The horse should not have even been on the launch pad, NASA grounds coordinator Nathan Mearson said. He ate a critical section of the ship, and it set us back a full day to rebail and retie that section. Mearson said that the horse was returned to NASA stables and given a suitable meal. Remnants from the department's long-abandoned all-hay Mars probe. Although some reports indicate goats have been gnawing at the ship's exterior cables, NASA scientists maintain that there was never a problem with goats. Explorer 1, NASA's first straw ship, was built in 1994, but after 11 months of painstaking preparation, it was destroyed the day before the launch when it unexpectedly rained. Explorer 2, like its predecessor, was headed for the sun, where it was to be the first spacecraft to land on a star. We'd hoped to bring back and study sun rock, Toshikima said. The straw ship had been equipped with a special reinforced wicker basket to hold the sun lava for its journey back to Earth. A straw-enforced robot arm was constructed to scoop the lava, which is reportedly as hot as the center of a nuclear holocaust, and place it into the wicker basket. The ship's debris is slated to be used as mulch. And there's our picture. It's the Amish space program. Good.
Is there like a day of mourning for the Amish?
You know, they deny the goats, but
it
was really the goats.
It was the goats.
To cover up.
It was a critical part of the ship. We just don't know if it was bailed properly. Okay, so let's look at this homework assignment. You were to write some sort of function where you passed in a period in seconds, and then we're asked what you want to convert it to, because it's commonly convenient for us not to necessarily say, well, you know, something is 0.00000041 seconds. That's not convenient. We'd rather say something like, I'm not sure how many zeros I just said, but let's just assume it was milli, or micro. Yeah, micro. Maybe it's 41 microseconds, something like that. All right, that's more convenient for us. So we want to write our own little converter for this type of thing so we can understand the patterns that exist over here in this power of 10 column. All right, so let's start. Here is that function I started you off with. So we're going to prompt the user for which other they want out of zeta, exa, peta, tera, giga, mega, kilo, milli, micro, nano, and pico. So that's going to be pretty similar to what we did down here. So I'm actually going to steal some of these lines. So we'll start off with our prompt. What would you like to convert to? And we're going to say zeta. Exa, peta, tera, giga, mega, kilo, milli, micro, nano, pico. And we're going to look at doing this a couple of different ways. All right, and then we'll go ahead and read in the choice as input dot next int will work. And then for right now, I'll just spit back out what the choice was. All right, so start with something simple so we can test this. And this guy's supposed to return a double, so for right now, I'll just return a negative 1.0, just so Java stops screaming about it. All right, we'll be adding some other stuff in here in a second, but for right now, all this function does is it creates our scanner for reading something in, prompts them with a little menu, reads in their choice, and spits their choice back out to the screen, proving it read it in. All right, kind of a good starting point to make sure everything's kind of working. So here's our function. We're going to go ahead and call it from main. Oh, here, before I even print it, I'm just going to call converter dot period in seconds. No, it's seconds to other. There we go. And here for right now, I'll just pass it in 5 seconds to that guy, even though it's not even using that value yet. So I'm passing it an input of 5. 5 is coming in as this value, seconds right here, which I'm not even using yet. I'm just giving them a menu and displaying their choice. So I'll go ahead and run this. There's my menu, and I'm going to go ahead and actually probably wrote the menu a little backwards. Probably want to display all that stuff first and then ask them what choice they want. Doesn't matter, but that'll look a little cleaner. What would you like to convert to? So we'll go ahead and pick 4, and it should just spit back out 4, proving it read it in. All right, so we're reading in our option now. So if they entered in 4, that means we want this guy in teraseconds, correct? Now, what's teraseconds? Go back to our slide set here. Tera is 10 to the 12th. So if I have 5 seconds, what should 5 teraseconds be?
A lot.
So how would you write it? So here, I'll throw an extra slide in here. So we'll say example. 5 seconds is how many teraseconds? Previous screen here. Here's tera, it's 10 to the 12th. So how would I write the equivalent of 5 seconds in teraseconds? Is 1 terasecond more or less than 5 seconds? It's way more, right? Kind of that's equivalent to asking which is bigger, 1 gigabyte or 1 kilobyte. It's even bigger difference than that. But seconds would be akin to kilobytes here, and gigabytes would be akin to teraseconds. So 1 terasecond is going to be, well, 1 second would have a representation in teraseconds that would be a fraction of 1, correct? How many zeros will I have? 11 zeros. So 5 seconds can be represented as 0. I think that's 11 teraseconds. Correct? Does that make sense? All right, so how did we get 5? How did we get this number from 5 seconds? What did we do to it? I'm going to kind of go through the process here like I kind of intended for you guys to do for the homework assignment. Well, just whatever. So we want to really explore how this math works. So let's say I wanted to do 5 seconds in, well, let's start with this. How do I convert 5 to this number right here? Divided by what?
1 to the negative 12.
Okay. What are the steps? What are the individual steps of that?
Divided by 1,000, 4 times in this case.
Okay, 4 times. Okay, or I could divide it by 10, 12 times, right? So we all said the same thing. Every part of what the answers there were the same thing. But if we're breaking it down to baby steps, I'm going to divide 5 by 10, 12 times. And that will get me to that number, correct? So, just for the sake of argument, we'll just assume that they entered in Terra here for the 4. So we'll hard code in that answer just so we can explore the math. So I'm going to do something. So since they put in 4, I need to do something 12 times. For int I is equal to 0, I is less than 12, I plus plus. And we'll say seconds is equal to seconds divided by 10. And then we'll go ahead and return the new manipulated version of seconds at the end. So it doesn't matter what we actually enter in as our answer here when it asks us which of these do you want to convert it to. We just assume that we entered in 4, my current version of the code. And then this is the math that should get us that exact same number. The 0.0000000000005. All right? Because we're going to divide by 10 that many times. Let's go back to test. And now, seconds to other is actually returning a value now. Here at the end, we're actually returning our value. So it's going to fire out of here like a double. That is a number. And I want to go ahead and print that. Now, for those of you who are currently in the 250 class, I would say within a couple of weeks, you'll have the overlap in there enough to kind of be ahead of me on this. But for right now, just trust that I'm showing you the lines of code that do something. Use them as little widgets. Kind of like I gave you a toolbox with a screwdriver in it and stuff like that. You don't necessarily have to know how something works, just that it works for right now. And then the dots will connect. Okay? So we're going to go ahead and call this function. This function boils down to a double because it returns a value, and I'm going to print out whatever that is. Go ahead and run that. It's going to ask me what I want to convert it to. We'll play along and enter in 4, but it doesn't really matter what I type in here. I can type in elephant. Oh. You can't actually type in elephant because I tried to get the next int. So don't type in elephant. Type in something numeric. So here, I'll type in a 9. That way it won't crash. And there is our 5.0 times 10 to the negative 12, which will be 0.11 zeros and then the 5. Make sense? Okay. What if I wanted to convert that 5 to zeta? I would divide by 10 how many times? 21 times, right? So I'll just go back into my code. Again, we'll hard code it. We'll assume they entered in 1 for zeta, and we'll say 21. Run this again, type in something numeric, and there's our zeta version of it. Now, what if I want 5 in milliseconds? How many milliseconds is 5 seconds? 5,000. And how do I get to 5,000 from 5? Or multiply it by 10 how many times? 3 times. Again, same thing, right? 10 times 10 times 10 is 1,000. Get it? All right, so if I want to go the other direction, I'm going to say less than 3, because if you notice from our chart here, Milli is 10 to the negative 3 power. The ones we were just dealing with were in the positive scale. 10 to the 12th, 10 to the 21st. So this is 10 to the negative 3. But so instead of divide, I'm going to multiply by 10. And now this should give me milliseconds, no matter what I type in. There's my 5,000 milliseconds. All right. So if I were to pass in, let's go back and look for our pattern now. If I were to pass in 5 for seconds and I entered in 1, we want to divide by 10 21 times. If I enter in 2, we want to divide by 10 18 times, 15 times, 12 times, 9 times, 6 times, 3 times. Multiply 3 times. Multiply 6 times. Multiply 9. Multiply 12. Make sense? How do I make this work generically? Well, let's start off with the hard-coded version of this. So we're going to read in our integer. We're going to say if the choice is equal to 1. Hello. Then what are we going to do? Well, we're going to do this guy. And we're going to do 21. And we're going to do divide. That's if it's a 1. Else, if it's a 2, we'll do that 18. Else, if it's a 3, we'll do that 15. Else it's a 4, we'll do it 12. Else if it's a 5, we'll do it 9. Else if it's a 6, we'll do it 6 times. If it's a 7, we'll do it 3 times. If it's an 8, we're going to multiply. Three times. If it's a 9, we'll multiply 6 times. If it's a 10, we'll multiply 9 times. If it's an 11, we'll multiply 12 times. And we can just trust that we put in one of those values. All right. So very much a brute force approach to solving this problem, where we put an if statement in, asking if we entered a 1, this is what we do. If they entered a 2, this is what we do. If they entered a 3, this is what we do. So on and so forth. So we'll go ahead and run this. If I want to convert 5 into zetas, I'll put a 1 there, run it. There's my zetas version of it. If I want to convert it into x's, I'll put a 2. There's my x's version of it. If I want to convert it into picoseconds, I'll put an 11, and there's my picoseconds version of. That make sense? So that would be a suitable solution to the homework assignment. Now taking it a step further, I don't remember exactly what I asked in the homework. Did I have you just do this, or did I have you go from frequency to period and then have that go in here? Or did I not necessarily specify?
I think it's-
Yeah, that's fine. So just as you take this a step further, we know this little chunk of code right here, right? That guy prompts for a frequency and asks us what that frequency is in and gives us a period in seconds, correct? This guy down here, he converts a period in seconds into a more appropriate base. So what I can do is I can actually take this value right here, and instead of hard coding in a 5, I can paste that guy in there. The value I'm going to pass the seconds to other is whatever value is returned by frequency to period in seconds. So now it'll prompt me. Go ahead and hit play. Please enter a frequency. We'll do 2.4. We're going to say that's in gigahertz. And how do we want that? We know that 2.4 gigahertz is going to have a really small period in seconds, right? So we probably want this maybe in picoseconds. So we have 416.66 picoseconds. A little bit easier to read than, probably the 0.00004166, whatever. Actually, it would be more zeros than that, but it would be 9 zeros, correct? I think, yeah. Picos to the 12th. So 9, it would be 9 zeros followed by 416. Would be seconds. All right, that makes sense? Now, something we should be looking for here, though, is a pattern. First of all, let's start with a pattern over here. With all these names, we keep seeing jumps by 3. -12, -9, -6, -3. What's between kilo and milli? Just plain seconds. So we still have a jump by 3 in here. It's just not represented on this chart, correct? And then jump by 3, 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 jump by 3. So if we wanted to write this to be a little bit more generic, we know our worst case is a base of 21. And we can subtract. If we have a base of 21, and we enter it in a 1, we're going to subtract 0 times 3 from the 21. If we enter it in a base of 2, we're going to subtract 1 times 3 off of 21 to give us 18. A base of 3, 2 times 3 off of 21. 3 times 3 off of 21. 4 times 3 off of 21. If we get down to so this is, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 10, that's actually 11, right? 11 times 3, which is 33 off of 21, gets us -9. Make sense? So we can actually write this in such a way that it is substantially smaller once we apply the pattern. So I'm going to come in here to our converter. And we'll just take away all that crap. And we'll say int base is equal to 21. And then we want to subtract from 21 the choice minus 1 times 3. Make sense? The choice minus 1 times 3. So that will get our base to the right value. Either 21 or 18 or -3, whatever it should be. But now we have another issue here. The next issue is, as we went down that list, we had to convert between dividing by a certain value and multiplying by a certain value. Dividing by 10 or multiplying by 10. to take into account going to the negative side. All right? But if we had a function that can do powers for us, which all of these are, this is 10 to the 21st power, 10 to the 18th power, 10 to the 15th, 10 to the 3rd, 10 to the negative 3rd power. If we had something that could solve that problem for us, we wouldn't need to worry about switching between division and multiplication. We can always just multiply. Now, we do have another issue in here. The other issue is that we really need to insert seconds between kilo and milli. Why? Well, because we have a jump of 6 here instead of a jump of 3. So, we come into our thing here. Eight is actually seconds. So if we take that, 8 minus 1 is 7. 7 times 3 is what? 21. 21 minus 21 is 0. 10 to the 0 is what power? 10 to the 0 is what value? 1. So seconds converted to seconds would still be seconds. There's 9, there's 10, 11, 12. And then ultimately we'll return seconds times math dot pow 10 to the base. So this is how we can take something to a power in Java. There's an equivalent power function in GameSolid. I'm pretty sure there's a power function in Excel. There has to be. All right, so now we should have all the work is done by these two lines because we noticed a pattern. Make sense? So we'll do our frequency, 2.4. We're going to say that's in gigahertz, and we want to convert that into gigaseconds, let's say. 0.416666, blah, 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 gigaseconds. 2.4 from gigahertz, and I want to leave that in seconds. That's the 9 zeros followed by the 416. That makes sense? All right, so there's kind of a pattern-based way of doing this. Now, realistically speaking, do we need to memorize all those things? Probably not all of them. I mean, it wouldn't hurt. But if you look at them, which ones, I mean, I realize we don't deal with frequencies and periods in time and stuff like that all the time, but at the very least we see things, listed in certain bases like this. Which ones have you seen before in any sort of common way? Have you seen zeta very often? No. Have you seen exa very often? Okay, what about peta? That's the kind of the one starting to creep in. And really, where do we recognize some of these things from? We reckon from storage space, right? Either hard disk space or RAM, system RAM. So, you really don't hear about petabyte hard drives yet, but it's spoken about in enough things that oh, that's what's coming next, right? Because now, what are we looking at? Right now we have tera, correct? A big hard drive today is like a 3 terabyte hard drive. That would be kind of our, on the larger side of a single hard drive. You might have people who set up hard drive arrays that have, several 3 terabyte drives together to give you something larger. But generally speaking, a 2 or a 3 terabyte hard drive is considered to be a fairly large hard drive today. 1 terabytes are pretty commonplace. Less than a terabyte anymore is actually fairly uncommon, except in solid state drives, because it's prohibitively expensive to get a solid state hard drive that is bigger than a terabyte. You're starting to see terabyte ones becoming somewhat commonplace. They're not so prohibitively expensive, but I don't think you could buy a 3 terabyte solid state drive. But you can definitely buy a 3 terabyte mechanical drive.
Side question.
Yep.
What do you think of the hybrids? Just
Um,
of them.
Well, I mean, the purpose of the hybrid drives, well, let's actually back up. The purpose of a solid state drive is it's supposed to be fast. Well, what do we mean by fast? Fast means when we measure the speed of our hard drive when we're using your computer, it has more to do with how fast applications launch, right? When you save a Microsoft Word document, that's going to be equivalently fast whether you're saving it to, I guess I don't want to say floppy disk, but almost. Whether it's a mechanical hard drive or a solid state drive. But when you launch Microsoft Office off of a solid state drive, it's going to launch more quickly than it would off of a mechanical drive. So the whole concept of the fusion drives or the hybrid drives is that you have all your application, your operating system and your application programs installed on the solid state side of it, and then all your just data stored on the mechanical side of it. Because that's not where you're not going to recognize speed when you hit the save button. From your perspective, when you hit save, it's pretty instantaneous, right? But when you double click on Office, now there's launch time. So that's the purpose of the hybrid drives. It's supposed to be, you're supposed to get the benefit of the performance benefit of the solid state without the loss of total capacity that you typically get with solid state because of the cost. Now the downside to it though is that you have a single drive that has kind of 2 hard drives in it, and one of those drives is mechanical, which means that it's going to have a higher likelihood of breaking down. So it's not going to be as durable. Inside of a laptop, one of the big selling points of a solid state drive inside of a laptop is there's no moving parts. So if you were in the middle of copying a large file and you drop that laptop, you're probably going to be fine with a solid state drive. If you're in the middle of copying a large file and you drop your laptop with a mechanical drive in it, almost guaranteed you just corrupted your hard drive. Some of the very modern laptops have some detectors in them, gyroscopic detectors that kind of can detect a laptop in free fall that just lock everything. Seriously, yeah. But if you're in the middle of transferring a file, I don't know if I'd rely on that. So if you're transferring a 5 gigabyte file between 2 things, I don't know if locking it's going to happen before the thing actually hits the floor. So it's a trade-off. I think for a desktop computer, the fusion drives make a lot of sense because you get to keep your capacity, but you still get the performance benefit for your software applications. When you think about those of you who have big hard drives, most of the stuff that's taking up your hard drives are your MP3s that you downloaded perfectly legally, I'm sure, your movies that you downloaded perfectly legally, data. Data is what takes them up. You haven't filled your entire hard drives up with hardware or with software applications. Even if you're a big gamer, the entire capacity of your hard drive isn't taken up by installs of games. It's all the data files related to those things. Make sense? So have your solid state drive for your applications and have your mechanical drive for your actual data. That's the trade-off. But I would say for a laptop, I would not buy a laptop today that didn't have a solid state drive in it. If you were buying one starting today. 2 years ago, solid state drives were still prohibitively expensive. Now you got to go with the trade-off. That a mechanical laptop hard drive 2 years ago was still pretty cheap. So, break my hard drive, make sure I have everything backed up in the cloud, drop $60. One arrives from Amazon tomorrow, pop it in, we're done. We're back in business. But from a maintenance perspective, I think solid state makes more sense today. That cover all your... What was I talking about before?
Quick side question.
What am I, Wikipedia? The answer is yes.
Wikipedia Live.
Wikipedia Live. It's like kind of like Siri. What was I talking about before that? Oh, right. Which of these is commonplace? So definitely Giga. We've been dealing with gigas for a while. We've been dealing with terabytes for a while now too. So tera, giga, mega, kilo. This would just be the equivalent of bytes if we were dealing with data storage. What about milli? We heard things references this is so many milliseconds.
Races.
Common, right? Milliseconds is a common term that we hear. So yeah, like running races, swimming, things like that. We're measuring time down to milliseconds, right? What about microseconds?
Not so much seconds. I think more size of things, or either tech related or
Okay.
other.
So it's a term you kind of hear, but really in terms of measurements, we don't really hear micro very much.
No.
You would get it with hardware like micrometers, things like that, but this is really something that's not as common. Nano is actually more common. Pico less so, but realistically, out of if we're going to look at all these and put them kind of in a pecking order, tera, giga, mega, kilo, definitely important. Seconds, fine. Milli, nano, and pico are probably more often used than micro. All right. So it's kind of the extremities that we can leave off on the high end, but certainly we're going to start getting into these, right? But how useful are these in terms of time? When would you want to measure something in zettaseconds? Well, when do we measure something in milliseconds?
You use that a second if it takes a really long amount of time.
Okay, well, so that's the answer to the first part of my question. So for milliseconds,
It's really short amount.
yeah, when the amount of time is so tiny, and we need to have a way of referencing millisecond to millisecond, comparing two different times, 3.22 milliseconds versus 3.23 milliseconds, something like that. Now we have something to compare. But so when we're dealing with very small measurements is when we deal with milliseconds. So zetta would be what kind of time period? Could be hours. Probably even bigger, right? So what if you're in a swim meet, and right now it's usually measured in minutes, seconds, milliseconds. Is that the breakdown for swimming? I think. I don't know why I picked swimming. I just I did. I guess I just like Phelps in a suit, right? That was supposed to be creepy. Mission accomplished. But how big does a time increment need to get before we start measuring stuff in zettaseconds? Days? So let's say you were swimming and the amount of time was exactly 25 days. In the measurement of 25 days in seconds. How many, so 25 days, that's 25 times 24 times 60 times 60. Is that the number of seconds? 25 days times 24 hours in a day times 60 minutes in an hour times 60 seconds in a minute. So that's our number. That's 2,160,000 seconds. All right. How many zettaseconds would that be?
That's still like megaseconds.
Yeah, not enough. So zettaseconds is going to have 20 zeros followed by this stuff, right? But it's going to start over here. So that's 1, 2, 3, 4, 5, 6, 7. So 13 zeros followed by that. That seems to be not even helpful, right? So that's 7 right there. So this is 21, this is 18, this is 15, 12, 9, this is 6. So this is 2.16 megaseconds. If we're measuring something in a swim meet that took 25 days to complete. Years?
Usually wouldn't be enough. Not to get to Zeta seconds.
Okay, so what would we use Zeta for? Is it kind of just our just-in-case value?
Future-proofing.
Yeah, future-proofing. I mean, isn't that true with Is that your Obama ringtone? Is there a story behind that?
No, it's my Facebook wall. Just making noise.
Oh, like somebody had one of the video that autoplayed in Facebook. Sorry, mom was calling. All right. So, could be somewhat future-proofing. If we think about our hard drives today, terabytes, 3 terabyte drive, how long do you predict it will be before we have a 1 petabyte hard drive for consumers? I'm sure companies have wired a bunch of mechanical drives together to create a 1 petabyte hard drive by now. But in terms of jumping into Best Buy and coming out with a 1.0 petabyte hard drive, how long? Huh?
Couple years.
Couple years?
Probably not a decade for consumers because consumer use-wise, it's not going to expand that
Okay.
much.
So does anybody think like 2 years is completely unreasonable? That might be a little on the aggressive side, but not unreasonable, right? It's plausible that we might have a 1 petabyte hard drive in 2 years. Yeah, I would agree with that. What about a 1 exabyte hard drive?
Let's get into the NSA.
1 exabyte is 1,024 petabytes. How long do we have one of those? Is that a decade? Well, we might say today, well, why do you need that?
Well, there's a universal cloud storage used by the entire world.
Well, but what keeps happening to our data? Doesn't our data keep getting bigger and bigger?
Yeah, it keeps getting stolen.
Keeps getting stolen, put on the internet.
So what you're saying is
And then
Korea
save
already
it.
has one of those, and they just keep filling it up with our shit.
Sure.
So let's kind of keep talking about data here. How many of you have ever watched TV or sports on a standard definition TV? How did we live? Would any of you actually watch a Packers game today in standard definition?
Well,
Not unless it was really good food being stored there.
Stored.
Stored.
like projectors and standard.
Okay, yeah, so it's an embarrassment, right?
It's 73 inches on the table.
But you shouldn't be. It's 73 inches of garbage. That's what it is. Okay, so standard definition used to be the standard, right? That was considered good. And then we came out with high definition. Well, what's high definition? That's the new standard. Okay? 'Cause now you have crappy high definition and then real high definition, right? Crappy high definition if you have like a 1080i TV. It's 1368 by 768 pixels. That's not even full HD. Full HD is 1920 by 1080, right? But even by today's standards now, that's not good enough. Now, what are the new TVs? They're 4K, right? People were already saying with 1080p, like the news people. Actually, 1080p created a whole new industry. Even 1080i, standard high definition TV, created a whole new industry in makeup. Because these people you used to think looked perfect, now you realize how much paint and stuff they have caked on because now you're seeing every pore, right? I really like the soccer injuries that you can see in high definition. Because now you can actually feel like when the bone goes through the skin, it's like you're there.
It's probably better than if you're there, because if you're there, then you'd be up in the stands.
Well, not I kind of run towards the mayhem. I'm that guy you see. They see me, they carting me out. It's like, oh, it's okay. I'm not a doctor, but I stayed at Holiday Inn Express last night. I can set that shin bone. So now we're going to 4K TVs, right? Now, keep in mind, we don't even have cable television yet that can reliably broadcast at full 1080p. We don't have that yet because the amount of data it has to move is ridiculous. Well, now we're just going to go and just make it 4 times that. I mean, we couldn't move it before. We really can't move it now. So what are they going to do? Well, they're going to come up with new highways to send the data. So they're already starting to use, well, for instance, you can get 1080p movies on Dish, DirecTV and stuff like that. The broadcasts aren't in 1080p, but you can do on-demand movies in 1080p because that's a dedicated download. The broadcasts are off a Spectrum radio that can only send so much data out at a time. But when you're dealing with cable, where you just have these giant wires going under the town and all the data's got to be shared on there. We've probably seen it at home if any of you have Time Warner cable or something where you were watching a show and you came back to your house and all of a sudden it said, press OK if you want to watch this channel. This channel's not available right now because there's too many people in your neighborhood who are watching other high definition channels. There wasn't room for this one. They just hope you don't complain, even though you're paying for the channel. So, that becomes a problem. But our data keeps getting bigger and bigger and bigger. How big's our music today? How big is one MP3? 5 megabytes. Okay, and MP3s are compressed. Okay, and now we're starting to move towards having less compressed audio formats because they're non-lossy audio formats, right? Formats where more of the original audio data is there. You don't have to reconstruct it. So it should sound more correct, less filler. And that's going to make the size of the files go bigger, correct? What about our internet connections? Do our internet connections keep getting faster? Generally speaking, yeah. You go back 5 years, the fastest internet connection 5 years ago was a lot slower than your fastest internet connection today. Go back even longer than that. In the early days of MP3s, people were downloading them over a 56K modem. It might have taken 40 minutes to download an MP3. Now, if that MP3 doesn't download in like 15 seconds, something's wrong with the internet.
Let's put some of the next source on there.
Yeah, you're screaming down the halls like, is FalconNet down for you? This thing's only going at 60K a second. People used to pay thousands of dollars for 60K a second. It's ridiculous. But our data needs keep getting larger and larger and larger. And now there's all this stuff we see on TV with streaming video, whether it's Netflix or any of these on-demand services, where now you sit there and you binge watch Doctor Who or something like that on Netflix, and in a single day you watch 15, 20, 30 episodes of Doctor Who. You can do 30, can't you? Yeah, but I think that's about the day. 30, but whatever. But in any case, I mean, that's a lot of data going across your internet connection, right? So the source of it is Netflix, but your internet provider is the one who has to provide that bandwidth to you. So that's why they're screaming that, hey, consumers don't want their internet bills to be too high because we have to be competitive on that side, yet Netflix is making it very easy for people to stream data and just maximize their connections, and how do we keep up? Somebody's losing money here, and it's not Netflix. And the consumers aren't going to pay any more money, right? You just want it to work, and you don't care who you have to step on for it for that to occur. But punchline with all this is our data keeps getting bigger and bigger and bigger. So our need for larger hard drives and stuff like that is going to go up, even if our real data, the type of applications that we use don't change. The quality of the content of those applications is what will change. As our computers get faster and faster processing, they'll be able to handle more pixels, they'll be able to handle more things dancing around the screen, higher resolution textures, all this other crap. So we're going to have to start moving into these areas for data storage. Now, kind of swinging this back to what we're talking about here in terms of frequencies, though, how does this play in? When will we ever need zeta seconds? When we're dealing with time. We mentioned that it might be just future proofing. But it's not like a week is going to get smaller. Right? I mean, time is kind of time. And the reality is most things that we're measuring go the other direction. We get more and more accurate. Our sampling of things happens more often. So instead of measuring something in the number of days, we're measuring something in terms of the number of picoseconds. So we can see how we can utilize that end of the spectrum. But on the other side, it's like we're moving away from that. So, we'll put that on hold, but constantly try to think about, is there an example where exa or zettaseconds really would come into play? Okay, just kind of think about that. All right, so questions about the homework. Kind of makes sense, see the pattern, how that stuff works. Okay, so how do human beings count? Well, so we're going to deal with some more conversion stuff. Well, we use base 10 because we have 10 fingers, 10 toes. It's easy to count, right? So base 10 supports the digits 0 through 9. Why won't this work for computers? The computers are stupid. God didn't give them 10 fingers. They're a lesser life form, right? Computers are based on digital logic. And digital means on, off. Yes, no. True, false. 0, 1. We don't have the capacity on a computer to conveniently count in base 10. We have the capacity to conveniently count in base 2. Because we can think of it as computers have 2 fingers. Okay, and then we duplicate those 2 fingers a whole bunch of times. So this won't work for computers, but it works for humans. Now we're talking about how do humans interface with computers. We like base 10. Computers like base 2. Well, base 2 numbers can become very, very scary very, very quickly. It's the number of digits. All right, so we want to talk about converting these numbers. So if we pick our favorite base 2 number, now at a glance, that's obviously what number?
4.
Oh, I can't enter it in as binary. That's a shame. I think that's where I ran out of. This only represents 64 bits. Is this less than 64? It is less than 64? I don't think so. Or it just didn't let me enter it in. Here, let's go this route.
Alice, go on
Google
there.
said no.
My guess
Go on
is
there
that
and search
Google's-
binary translator, and then you can enter it.
Now, Google can usually do this.
There. E,
That's not. No, that's not even right. Yeah, let's go. Yeah, it's pretty bad. Okay, Google can't even handle, because Google can handle smaller numbers. So if I put in a number 110111, binary to decimal, I thought Google usually just automatically does it. Does it. Isn't Google does it? All right, so that's decimal 55. All right. Now, in any case, point is proven. Google couldn't handle it. Google couldn't does it. This is not a convenient numerical representation for human beings. But it is a convenient numerical representation for computers. Computers could go right through that, no problem. Okay? But now we need to have a way for us to interface between what we're doing, whether it's through software or hardware, and the computer. All right? So, just for the sake of sanity, just kick this down to a little bit smaller number. So if that is the base 2 binary representation, what is that number in decimal? So we're going to talk about some different ways of converting numbers, and then we're going to look at some shortcut ways of converting numbers. So 110111 from binary to decimal. How do we do that conversion? So this is 110111. So that's our number. This is the 2 to the zeros place. Oh, come on. 2 to the ones. 2 to the twos. 2 to the threes. 2 to the fours. 2 to the fives. Oh, just killing me. All right. Or, what the heck? There we go. This is the ones place, the twos place. Just complete incompetence. The fours place, the eights place, 16s, 32s. Okay, so 2 to the 0 is 1, 2 to the 1 is 2, 2 to the 2 is 4, 2 to the 3 is 8, 2 to the 4 is 16, 2 to the 5 is 32. So to actually do this math, we would do 1 times 1 plus 2 times 1 plus 4 times 1 plus 8 times 0 plus 16 times 1 plus 32 times 1. So that's 32 plus 16, which is what, 48? 52, 54, 55. So this is 55 decimal. That makes sense how we did that conversion? All right. Now, if we wanted to write a program that did that, how would we do it? What would the logic be? What's the pattern of converting a binary number into decimal? So we always start from the right-hand side, correct? Move to the left-hand side. Each time we're taking the base in every single one of these is 2. And we're just increasing the power one at a time. 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3, 2 to the 4, 2 to the 5. Make sense? And then we're just summing up our values. So if we're going to read in a number, enter a binary number. Go ahead and steal our scanner line here. The num is equal to input dot next line. That'll give it to us as a string. And then we'll go ahead and just spit it back out to prove that it's working. And again, we'll return -1 for now, so Java stops screaming. Okay. And we'll go ahead and test this real quick. Converter.binary to decimal. Go ahead and hit play. Enter a number 110111, and it should just spit it back out, proving that we read it in. All right, well now we want to manipulate that. We want to take that binary number that we just read in as a string, whatever that means, and we want to turn it into the decimal equivalent. We'd like to spit out, in this case, a 55. Okay? In order to do that, we need to walk that string one character at a time from the end and accumulate an answer. So this is 1 times whatever's in this place, plus 2 times whatever's in this place, plus 4 times whatever's in this place, plus 8 times whatever's in this place, plus 16 times whatever's in this place, plus 32 times whatever's in this place. So the current place I'm at starts off at 1 and keeps doubling each time through, right? So we can build that pattern in. And how many times do we do this? We do this for the number of characters in this. So in this case, there's 6 characters, 6 digits, 6 bits we have to work through. Leave it like that for right now. Actually, let's start at the end since we're going to go that direction anyways. The num dot length minus 1. Keep going as long as it's greater or equal to 0. And subtract 1 from it each time. And we're going to have an integer here called place, and we'll start place off at 1. And we'll just print it out, system.out.println place. Then we'll say place is equal to place times 2. So it should go from 1 to 2, 2 to 4, 4 to 8, 8 to 16, 16 to 32. So in this particular case, the biggest number we should see is 32. It gets printed out. Enter in our number, 110111. There's 1, 2, 4, 8, 16, 32. If we went to enter in a much larger number, 65,536 is the last place from that one. Make sense? All right, now as we go through here, we're just printing out the places, but really we need to do some math. So we're going to say int sum, start that off at 0. If the num dot char at I is equal to the character 1. If I'm currently looking at a 1, the current position in my my string. So the character at the current position, if that's a 1, then I'm going to add place to my sum. Place doubles every time regardless. And what pattern is that? That's this pattern. Come back here. Is this a 1? Yes, so add my place. Is this a 1? Yes, so add my place. Is this a 1? Yes, so add my place. Is this a 1? No, so don't add this guy. Is this a 1? Yes, add the place. Is this a 1? Yes, add the place. Now, why did we just say add the place? Well, because 1 times 1 is 1. 1 times 2 is 2. 1 times 4 is 4. 0 times 8 is 0. Well, whenever we had a 1 up here, we always just added the place. It was only when we hit a 0 did this guy not matter. That make sense? That's only a truth for binary. Because we can just say 1 times 1 plus 1 times 2 plus 1 times 4 plus 0 times 8 plus 1 times 16 plus 1 times 32, and the math will work out. But in this case, we're looking at characters. Our binary number is being read in as a string, which is a collection of characters in our Java program. So we're going to say whenever I'm looking at a 1, let's just go ahead and add onto my running total whatever the current value of place is. And then we'll go ahead and double place for next time. And then in the end, let's return sum. So now in test, we can print that out. System.out.println. Whatever converter.binary to decimal returns. So enter a binary number, 110111, gives us a 55. And we're actually printing it an extra time inside here. That's this guy right here, where we just spit it back out, proving we read it in. Similarly, we can enter a much bigger number, 110, and that's the number 3,543. All right, so very simply, we're able to write a snippet of code that asks the user for a binary number and converts it to decimal. What we'll do on Thursday is we'll go the other direction, write some code to do that. Then we'll make this a little bit more generic, which some of you have seen before, but still it's good for where we're going with this because most of you have not seen the next step. Then we're going to look at an even easier way to convert between binary and we'll look at binary coded decimals. We'll look at how to convert between binary and hex directly. Very interesting stuff. That'll answer the question why binary and hexadecimal tend to be the common denominator for computers. Human beings see things as hexadecimal numbers. Computers like things as binary, and we're able to jump back and forth between those two very easily using something called niblets. Niblets.
Sounds like
They're actually called nibbles. But all right. So I will see everybody on Thursday.